All right, everybody, welcome. Today we're going to dive into one of the most important charts in all of science. I'm talking about the periodic table. Now I know, it can look a little intimidating at first. But trust me, by the end of our little tour today, you're going to see it for what it really is. A map to everything.
But first, let's start with a big question. Just imagine for a second that you had to organize all the basic stuff that makes up our universe, all 118 different kinds of it. I mean, you've got gases, you've got shiny solids, you've got stuff that's radioactive. How would you even begin to sort all that out? It's a huge puzzle.
So, here's our game plan for today. We're going to see how scientists solve that puzzle. We'll start with the big picture, our map to matter. Then we'll zoom in and learn how to read an element. We'll explore the different neighborhoods on the table. And then we'll go even deeper, right inside the atom. We'll meet some of the atom's relatives, and finally, we'll see how all of this shows up in your everyday life. Okay, let's get into it.
So scientists had this problem, 118 known elements, these unique types of atoms. They needed a system, a way to organize them all. In the periodic table, that was their absolutely brilliant solution.
This whole thing really gets started way back in 1869 with a Russian scientist named Dmitry Mendeleev. And get this, the story goes that he actually dreamed up the basic layout. Now, of course, the table has changed a bit since then, but the fundamental idea is exactly the same. We arrange all the elements by their atomic number, which is simply the number of protons they have. It's such a powerful way to organize everything.
Okay, so we've got the history down. Now let's zoom in a bit. We're going to learn how to read this thing. I want you to think of every single square on the table as a unique address for an element, and it's packed with all the key information you'll ever need.
The very first thing you'll see, and maybe the most important, is the atomic number. This is like the element's unique ID number. It tells you exactly how many protons are in its core. And here's a pro tip. In a neutral atom, that number also tells you how many electrons it has. No two elements share an atomic number. It's what makes them, them. Next up, you've got the chemical symbol. This is basically the element's nickname, just a 1- or 2-letter abbreviation that scientists use as a shorthand. Now, some of them are super obvious, right? C for carbon, but others are a little tricky, like Au for gold. You know why? It comes from the old Latin word for gold, Rm. Pretty cool.
And of course, you've got the element's full name written right there. Pretty straightforward, right?
And finally, we have the average atomic mass. This is the average weight of one single atom of that element. Now, you might be looking at that word average and thinking, wait, why is it an average? That is an excellent question. And it's because not all atoms of an element are exactly the same. We'll circle back to that in just a bit.
All right, now that you know how to read an element's address, let's zoom back out and explore the whole city. You can think of the periodic table as being organized into different neighborhoods. And believe me, each neighborhood has its own totally unique vibe.
So the table's layout is all about rows and columns. The horizontal rows are called periods. As you just move from left to right across a period, each element adds one more proton and one more electron. That's it. But the vertical columns, those are called groups, or, and I like this name better, families. And just like a real family, all the elements in the same group have similar personalities. They share similar chemical properties. They just act alike.
You can also split the table into 3 main zones. On the left side, you've got the metals. You know them. They're shiny, they conduct electricity. Over on the right side, you'll find the nonmetals. They're pretty much the opposite. And then, kind of wedged in between, you have the metalloids. These are the rebels of the table. They can't quite decide if they want to be a metal or a nonmetal, so they end up with properties of both.
Okay, now for the fun part. We know our way around the table, so let's put that knowledge to work. We're going to play atomic detective and figure out exactly what's going on inside a neutral atom using just the info from its little square.
So, we already know the atomic number gives us the number of protons and electrons. But what about the neutrons? Well, turns out it's a really simple 2-step recipe. First, you take the atomic mass and just round it to the nearest whole number. So for calcium, 40.08 just becomes 40. Then, for step 2, you subtract the atomic number from that new rounded number. So 40 minus 20 is 20. And there you have it. A neutral calcium atom has 20 neutrons. See? Not so tough.
Okay, so remember that little cliffhanger I left you with about why the atomic mass is an average? Well, it's time for the big reveal. Let's meet the atom's extended family, isotopes and ions.
So what in the world is an isotope? They're basically different versions of the same element. What makes them the same element is that they have the same number of protons, but they have a different number of neutrons. And because neutrons have mass, this means they all have a slightly different atomic mass, a different weight.
Hydrogen is a perfect example to look at. It's got 3 main isotopes. Now, they all have 1 proton, which is what makes them all hydrogen. But protium has 0 neutrons, deuterium has 1 neutron, and tritium has 2 neutrons. See? They're all members of the hydrogen family, they just have different weights.
Now, atoms aren't always neutral. They can also gain or lose electrons. When that happens, they get an electrical charge, and we call them ions. Here's an easy way to remember the two types. If an atom loses a negative electron, it becomes more positive. We call that a cation, and I always tell my students to think of a cat with its paws. They're positive, get it? And if an atom gains a negative electron, it becomes a negative anion.
All right, so we've gone through a ton of stuff. But now we get to the really important question. So what? Why does any of this matter to you? Well, the truth is, these elements are all around you, every single day.
Seriously, you interact with these things constantly. The aluminum in the pan you use to cook breakfast, that's an element. Any gold jewelry might be wearing? Element. Carbon is what makes up diamonds. The sodium that's part of the salt on your fries. The iron that makes the steel in bridges and buildings. It's all right there on the table.
And what about those special isotopes we were talking about? Ugh, they have some unbelievably cool jobs. That americesium-241 in your smoke detector, that's an isotope keeping you safe. The uranium-235 that fuels nuclear reactors to generate massive amounts of energy, also an isotope. And this one is my favorite. The long-lasting batteries that power NASA's spacecraft exploring deep space, they run on plutonium-238. How cool is that?
So there you have it. That's our tour. The periodic table is so much more than just a chart in a textbook. It is a map that helps us understand the entire universe. And the amazing thing is, we're still figuring out new ways to use it. So I'll just leave you with this question to think about. We already use these elements and their isotopes to power spacecraft and save lives. What's the next big problem we're going to solve with them? The possibilities are literally endless.